Okay, so hello everybody, good evening. I'm Ángel Muñoz, my college is Mario Fernández, and we are working in the University of León, in particular in the Research Institute of Applied Science in Cybersecurity. So our talk is going to be about an algebraic or a matrix approach to the level of redundancy of certain databases, okay? This is a joint work with Noemi de Castro and Miguel Carriegos, and it's a little part of a project that started some time ago, okay? So the talk is going to be divided into different parts. The first part, which is I'm going to handle it, is going to be a brief introduction for the theoretical concepts I'm going to use. And the second part is going to be a practical part. So Mario is going to show you some results that we have gotten from some real databases with cybersecurity reports, okay? So to start with, I'm going to briefly describe the graph structure of the databases we're working with, okay? So, well, for me, a database is just a table with rows and columns, and the columns have labels. These are the column names, the variables, and the rows are just the data you are collecting, right? Whatever information you are collecting, and well, usually people use the information below the column names to get some knowledge about the columns and the relation between the columns, right? So here instead we are going to use the column names, not just the names, but the meaning of the names, to get some prior knowledge of our database, okay? And some information about the relation between the variables, okay? So, for example, we can find in our database variables as house price, house size, house neighborhood, okay? And we can use the word house, for example, as a categorical word, okay? Representing a smaller single table. And then the words price, size, and neighborhood are just variables of this smaller table, right? In this way, we get a tuple or vector of little tables, little databases. And the point is that there is a natural way to give to these kind of things a graph structure, okay? So our nodes is going to be both the categorical words, right, and the names of the variables. Here names represent, as I said, the categorical words. For example, in this little example that I gave to you, house is going to be, for example, name 1. And price, size, and neighborhood are going to be column 1, column 2, and column 3, for example, right? And we have an arrow between name I and column J. If column J belongs to a table representing the categorical word name I, okay? This can be quite general, and there are just 3 rules to have to get our main object, okay? Well, so the point is that we want to give a complete algebra description of one metric. The metric is the level of redundancy of our database, okay? And in order to do so, what we're going to do is to use this structure to transform completely our database, okay? So recall that given a directed graph, we can always get its associated adjacency matrix, right? We have a 1 if the corresponding column belongs to the table corresponding to the categorical word name, right? And in any other entry, we have zeros, right? Well, this gives completely, or describes completely the graph structure of our database. And the point is that we can encode the rows, the information that we have collected. We can transform it we can transform these rows into a matrix with this structure, okay? So this is what we call the weighted matrices, and we can get a weighted matrix for each row, right? When we have a 1 in the adjacency matrix, then we put into this entry the corresponding entry in the original database, okay? Well, as I said, the point is to describe completely, in a complete algebraic way, the level of redundancy. And the trick or the key point to do that is that when we transform or we drop a variable, then the adjacency matrix is transformed, okay? We change a 1 with a 0, okay? So it leads to a different directed graph and a different adjacency matrix. Here we have considered these 4 redundancies, of types of redundancies, right? But we are going to use, in the simple example after, just the 3 first ones, okay? So we can compute, as I said, the level of redundancy in this way. It's going to be the norm 1 of the original matrix minus the norm 1 of the transformed matrix divided by the norm 1 of the original matrix. If we want to compute the total level of redundancy, we have just to sum up all of these quantities, okay? So this is the theoretical part, and now Mario is going to explain you what results we had in a real database.
Thank you, Ángel. Good morning. Welcome to the talk. We're going to see now how all the concept that my partner Ángel has explained has been applied to our tool. The tool has been coded in Python 2.7. It has been called RIAS tool for removing redundancies. And it has 3 main features. The first one, it allows the user to remove the 3 types of redundant variables that he just mentioned, computing the total level of redundancy. Second, it can work in 2 different ways. A single one, in this case, the user can remove only 1 type of redundancy each time it uses the application, and the cumulative one. In this case, we can concatenate several types of redundancy, and we can delete them at once. And finally, the tool is going to generate a graph with graphical information about the variables in the cleaned database. This graph is generated according to the recognition of variables. The recognition is going to be automatic. In this case, the variables are going to be identified only by the separator between names and columns, or manually. In this case, it's the user who makes a previous distinction in a semantic way. So attending to the general working flow of our application, we're going to start always with an input database that we introduce in the tool in order to process it. And when the process has finished, we're going to obtain always 4 outputs. The first one is going to be the graph of that initial database. The second one is going to be a new database clean, a database without the type of redundancies the user wants to remove. The third one is going to be a graph that corresponds to that clean database. And finally, a report that gathers all the information about the redundant variables that we have removed, and also information of the level of redundancy that we have just eliminated. We have been lucky because we had access to a real cybersecurity database that was composed at the beginning by 363 variables divided between isolate names and names with columns. We have introduced the database in our tool, and we have generated the first initial graph. That is the graph that we are seeing on the screen. The green nodes represent the names, and the yellow one represents the columns. This is the aspect of the new graph when we have eliminated the redundancy of type 2. Small variations here because there is a small percentage of this type of variables in the initial database. This is the representation of the graph when we have removed the second type of redundancy and the third one. We have here a small number of nodes than in the previous one. And finally, if we concatenate the 3 types of redundancy, we're going to obtain a more clear graph in which there are no redundant variables. So at the end, we're going to obtain a new database, in this case with 131 variables. We have reduced a lot of the initial number. And also, we are going to obtain the total level of redundancy, the 64% of the initial database. The tools are available to download them in our repository, and you can follow also us in Twitter. So thank you for following us.
Thank you very much.